So, good morning, everybody. I'm a member of the MAGIC and the LST collaborations. So I will try and tell you what we do with Pulsars. We also have a special guest, Ludwig is here. He doesn't know why, but he's here. So, yeah. A brief introduction about gamma ray pulsars and why we care about them. I briefly an overview to say also yesterday we know roughly 300 gamma ray pulsars at energies above 100 MeV. Most of them are from Fermi-Lat. We know that these gamma rays are produced via synchrocurvature emission in the magnetosphere of the pulsar. For two of them, at least, we know that there is also an inverse component scattering. So essentially, the accelerated electrons in the magnetosphere hit a photon with a lower energy and upscatter this to higher energies. For this, we need to assess and understand where exactly the acceleration in the magnetosphere of the pulsar happens. And we don't know this exactly. So there are several models that have been put forward in the years on which region could, in which position in the magnetosphere there could be this acceleration of the particles. We don't have much data to constrain them, yeah? At least at the energies that we are interested in. There is also a process here, I wrote it, that would absorb the very high energy emission from pulsars in the magnetic field. This is classically impossible. It would violate the conservation of momentum, but in a strong magnetic field, this can also happen, and therefore absorb the gamma rays that are immediately produced. So there are these kind of two processes. One of these two produce gamma rays, and this one will absorb them. So there is a sort of a equilibrium between the two to understand what is happening. Regarding the very high energy ones, I define here very high energies to be above 50 giga electron volt. For your reference, I think 40 giga electron volt would be something like 10 to the 25 hertz. Yeah? We know only 4 pulsars that emit above these energies and that we can observe from the ground. These are Ceribella, Geminga, and recently also B1706. CRAB doesn't need an introduction to this audience, yeah? So let's just say that the nebula, the CRAB nebula that we observe for us in the field is a standard candle. We basically use its spectrum to calibrate or to check the calibration of the instrument. This Geminga, it's a bit different because it's radio quiet and it's also much older, yeah? Recently in the community, in the very high energy in the astronomy community, this was raised interest about the subject because it was found that it is embedded in a vast halo of tera-electron volt emission. As you can see here, these are all young spin-powered pulsars. Okay, going to the MAGIC telescopes very briefly. I won't go in the details on how we detect gamma rays from the ground. If you're curious, I can tell something about this later. We have these two telescopes, 70 meters each, at the Canary Island of La Palma. Our energy range extends from 30 giga electron volt to 100 tera electron volt. So there is an overlap at the lower energy band here with Fermi-Lat. In the recent years, the MAGIC collaboration worked to improve this energy range and to make it accessible to lower energies here and also to higher ones at the top. Our best sensitivity is a sweet spot that is around 1 tera electron volt. Yeah? So I have here a brief historical overview of what we did with these telescopes. The MAGIC telescopes are roughly 20 years old. Yeah, we had in 2008 the discovery of pulsed very high energy emission from the CRAB pulsar above roughly 25 giga electron volt. This excluded at that time the polar cap emission model because the magnetic field close to the to the polar cap is too high, and it would immediately reabsorb these gamma rays that are produced at these energies. We were not alone in this business. Our colleagues of Veritas from America also observed the crab pulsar and saw that the emission extended up to 100 GeV. Then with improving statistics, we could do some studies of the light curve and see that the pulses get narrower as the energy goes up. We were searching for emissions from another pulsar with our previous technical instruments. At that time, we didn't see anything. Then essentially it was a race towards higher and higher energies. And the last update that we had on the crab was in 2016, when we found that the emission extends up to tera electron volts. The spectrum that you see here, this is the Fermi part of the spectrum. What we see is a sort of a continuation, but it is a power law. There is no cutoff in the spectrum. This is indicative that there is this inverse quantum process happening in the magnetosphere of the pulsar. Okay, coming to what I wanted to present in this presentation. This is our most recent result in the field. We've observed the Geminga pulsar, and we detected a very high energy emission from it with a good significance. You can see, you can compare here our light curve with the Fermi lat, where you can see basically the differences between MAGIC and Fermi, or Cherenkov telescopes and Fermi. We get many more events here, but the background is enormous. These are cosmic rays that enter the atmosphere and that are difficult for us to disentangle from the emission of gamma rays. What we found is that the emission in this pulse here is in phase with the Fermi-Lat one. This also proved that with this technology of Cherenkov telescope, we can go very low in energy and essentially be complementary to Fermi-Lat in some sense. I put here a reference if you want to go and see the paper. Coming to what we observed in the spectrum of Geminga, essentially we also saw a power law from this P2 pulse, extending from roughly 15 GeV to 75. What was a bit a surprise that it is very straight. There doesn't seem to be any indication for curvature in the spectrum, so like it is curving down. Yeah. However, the spectral index in this range is very, very steep. It's 5.6, so it's falling down really, really fast. Yeah. There is an excellent agreement in this band here between MAGIC and Fermi, which was something nice. It's not expected that two completely different instruments with different detection techniques agree so well in the energy, but this was the case. So here, just to make sure I did not scale up and down the points for them to match. Yeah. Essentially, with our result, together with Fermi, we can exclude the purely exponential cutoff that was introduced yesterday by Colin with a very high significance. And we also have a tension, however, not too significant, not enough significant with the sub-exponential cutoff model, that is this red curve that would be produced by the superposition of many of these ones. Yeah? So as I said, we run a maximum likelihood ratio test, and so that our data doesn't suggest that there is a need for any type of curvature in the spectrum to improve the model. Yeah? What we did was to try and have a look at a sort of classical model for this pulsar emission. The outer gap one would be this region, close to the light cylinder, but within the light cylinder. And we found that it cannot accommodate our emission here with the synchro curvature radiation. It needs to it needs to invoke an inverse quantum component to do this. However, you can see it clearly also here. By doing this, it can kind of be adapted or heavily modified to explain this emission, but it doesn't really fit well. You can see also here the GeV fluxes at some point where we have the most precise data from Fermila are deeply underestimated. So the idea is that probably this model either needs a profound review or there are alternative scenarios for the emission of these objects. And such a scenario came out recently. Here there was this paper by Alice Harding. There is a sort of a novel class of models for the emission of these pulsars, the so-called the current sheet emission models, where the emission comes also from close to the light cylinder, but a bit beyond it, yeah. And with these models, we don't need an inverse quantum component to explain the radiation. It can be explained by synchrotron radiation. It does predict an inverse quantum component, but at much higher energies and much lower also. So this would be a difference that two models have in the modeling of our data. So this was more or less the idea. As I said, what we are doing is we are observing these objects. We have less than a handful of them, only 4. So we can't really do much of a population study on them. Geminga, when it was discovered, became the 3rd one. So it was an important step forward. It is also the oldest today. We see a good agreement in the overlap between the spectra with Fermi. The older class of model predicts inverse quantum emission with some weird and heavy modifications. The new class of models can represent this emission better. So it is an interesting target also for the next generation of Cherenkov telescopes. We already have one of the CTA telescopes at the same site as MAGIC. And hopefully, but I can't say much more about this. We can also try and improve our set of pulsars to do a bit more. Yeah. Thank you very much.
I think we have time for a couple of questions. When you showed the spectrum, the magic spectrum of Geminga, is it? Did you take what did you take for Fermi spectrum? Is it the phase resolved spectrum or the overall spectrum?
The phase.
The phase resolved
for the same phase. Yeah, for the same phase where we took also the magic one, because here the spectrum that we see comes only, the emission that we see comes only from this narrow region, essentially the second pulse. So the Fermi spectrum that we used is the one derived from the same phase region. Yes.
So those are both, so to say, phase results.
Yes.
Great. Thanks.
Do you learn something from this detection or about the radio absence? Does this constrain somehow any of the models made to explain why Geminga doesn't show radio emission?
So if this outer gap model, more heavily modified outer gap model, was the case, so if the emission is inverse quantum radiation, essentially to produce such higher energies with the magnetospheric properties of Geminga, you need the electrons to have a head-on collision with the photons. So in this model, the very high energy emission that we observe comes from photons, from electrons that were accelerated towards the star and upscattered photons that are going the opposite direction to our line of sight. To be able for this to be observed in phase with the high energy components, it means that basically the pulsar is 90 degrees tilted. So this would be a prediction of this outer gap model that we could potentially check against the data.